Hey, welcome back to EC 382. This is a module 17, and we are going to study control systems. Okay. So we have a robot, and then this is a system, and then this robot has inputs and outputs. Okay. So in our case, the inputs, one of the inputs is a PWM. PWM to motors. Okay, we have two PWM signals, and the output is the speed. Okay, speeds of the wheels. Okay, so far then we have given the inputs or in this case PWM duty cycle to the system. We can find the speed, right? So when you say find, that means we can measure, okay, or we can estimate or predict, okay, mathematically or experimentally, right? Then module 17 goal is given the desired speed, okay, or desired output, we want to find the PWM duty cycle. Right, or input to the system, right? And this is called an inverse problem. Okay, for example, a forward problem is given f of x, which is in this case a cosine x squared plus sine 2x. Find f of x given x equals pi. Okay, well, this is a pretty easy problem to solve. Okay, the inverse problem, on the other hand, is given the same f of x, find x such that f of x equals 0. Okay, so in general, this is a hard problem. Okay, so this is what we want to do. Okay, so again, then what we have done so far from module 14, 15, 16, so we have an input, okay, and then we measured the output, right? And then with this module 17, so given desired speed or output or some other behaviors, then we want to find the appropriate input to the system. Okay, that is the goal of module 17. Okay. Right, then what is control systems? So let's define first dynamical systems. Okay, so we want to find the output. Okay, in this case, maybe for this moving vehicle, so the output is a velocity. Okay, and this RLC circuit, the output can be the current, right? The induced current flowing through the circuit. And given the input, okay? So the first case, the input is probably the force applied to the vehicle. And then, or in this RLC circuit is the supplied voltage to the system, okay? This is the input. And the dynamical systems are usually described by differential equations, right? And then the control systems is we want to find the input to the system. So in this case, f of t, the force, or the supplied voltage, okay, to achieve a desired output, right? In this case, the velocity of the car and or the induced current. Okay, right. So there are many applications, a lot. So robotics, electrical systems, computer networks, mechanical systems, industrial engineering, chemical processes, economics, and then even business operations. Okay, right. So let's take a look at this example, right? So we want to build a cruise control system. Okay, so basically we want to maintain a constant speed of the car, right? And then suppose that we know a 50 Newton of input force will drive the car at 40 miles per hour. Okay, right? So that means if you apply the force to the car, right, and 50 Newton of a car, okay, all of a sudden we just apply this force, right? And then the speed is going to be something like this, right? And then at some point it is going to be 40 miles per hour, right? And so this is the velocity, Vt, right? And maybe it takes takes long because we have a constant the force. So maybe let's say it takes about 20 seconds. Okay, and then and sometimes we have different friction. Okay, or sometimes we have a disturbance, such as this kind of a hill, right? And then all of a sudden the velocity will drop like this, okay, because of due to disturbance. All right, so even though we know a 50 Newton input force will drive the car at 40 miles per hour, then if you have a certain disturbance like this, or if the car is making turns, then we have a different friction. So, right, the friction force will change, and then we cannot maintain a constant speed, right? So this is not really a good cruise control system, right? So what we want to do is, what we really want to do is we want to maintain a constant speed regardless of disturbances. Okay, and this is called usually this is called disturbance rejection. Okay, and we also want to improve the response time. Okay, so it takes 40 seconds to reach 40 miles per hour. Okay, I don't like this. Right, so maybe like from 20 seconds to perhaps 5 seconds. Okay, so is there a way to do this? Okay, apparently, okay, so there is an easy way to achieve this goal, right? So it is called feedback control, okay, or closed loop control. So a system is called closed loop or feedback control if the controlled output signal is measured and fed back for use in the control computation, right? So if you have an input and output, right? So this is called open loop system. This is what we just discussed in this slide. Okay, so this is the open loop system. The closed loop system is basically we want to measure the output. Okay, so this is an output or like a sensor output. Okay, and then we want to measure it, and then we want to feed back to the system. Okay, and so this block here, we want to call it controller. Okay, so the goal is to design a controller that makes y of t. Okay, so this is y of t. This is a sensor output to be r of t. So r of t is our reference or desired. Okay, so reference input or desired input, which is r of t. Okay, so in our in the previous example, then the desired velocity was 40 miles per hour. Okay, so that is our reference input or desired input. Okay, and then the system output or sensor output, okay, which we can measure, that is y of t. Okay, in the previous example, it was v of t, the velocity. Okay, and the goal is again that we want to make y of t to be the r of t, right? So you want to make v of t in the previous example, the output or sensor output, okay, to be the same as r of t, okay, or the desired velocity vd, which is 40 miles per hour, right? And then, so this signal here, this is called E of t. This is an error, okay? And then it is defined as E of t is Vt, the desired input or reference, minus the sensor output. Okay, so our goal is to make this error to be 0. Okay, so this is the same as Vt equals 0. Okay, so this is our goal. Okay, so basically we wanna design this controller, okay, to make this error to be 0. Right? So that is what we want to do in a closed loop control system. Okay. So let's take a look at one example. Okay, so this is probably like the very first more like modern control system, which is called centrifugal governor, which was designed by James Watt, okay, for his steam engine, right? So it controls the speed of an engine, in this case a steam engine, by regulating the flow of fuel or steam, right, to maintain a constant speed, right? And it uses the principle of a proportional control that we're going to discuss soon. Okay, so proportional right? Okay, so the way it works is basically we have a speed sensor. Basically, this one is the drive shaft is connected to the steam engine. Okay, if the shaft rotates fast, then then due to this centrifugal force, these two oops, what's going on? These two oops, something's wrong. Okay, these two fly balls is going to move away. Okay, and then that will bring this this lever down, right? And then this one is going to go up, and then that can change the angle of the valve, right? So if the speed is greater than desired speed, okay, which means that these two flying balls are going to separate, right? And then eventually it is going to close the valve, this valve. If the speed is less than the desired speed, okay, and then the flying balls are going to move, together to the center, right? And then the valve is going to move down, and then eventually the valve is going to be open, right? So if the speed is the same as the speed, then it will just leave the valve as it is, right? So this is how feedback control or proportional control works. Well, another way, another example is then when you take a shower and then you're gonna, sometimes you wanna have the water is too hot or too cold, right? And then your body is basically a sensor, right? And then you feel the temperature, and then you just make adjustment of the temperature of the water. Okay, so that is feedback control system. Okay, so let's look at you know a little bit more about proportional control. So and so basically a correction is applied to the controlled variable, which is proportional, to the difference between the desired value, which is R of t, and the measured value, okay, which is y of t. Okay, so the controller is basically, we want to find the input to the system, right? So we want to find U of t. This is the direct input to the system. In our case, it's probably just a PWM duty cycle. Okay, that is the input to the system, and the controller is the function of the error. Okay, and then using this error, and then we want to find the input to the system, right? So the proportional control is the simplest control method. Okay, so this is really just either proportional to the error, okay, or Kp times R of t minus y of t. Okay, so this Kp, this is a constant gain, which is proportional to the error. Okay, and then this is proportional control, right? So the equation is going to be U of t, so input to the system, right? Here input to the system is Kp, a constant, right? So a constant gain that you need to find, times E of t. Okay, so this is a proportional control. Okay, right. Then let's take a look at this example. This is program 17.2, right? So we don't use the IR distance sensors. The robot run in the middle of corridor, right? So here we're gonna use the IR distance sensors. So let's call this one. This distance is DL, okay, for the left sensor. And let me call this one is DR, right? And then omega L is the angular velocity of the wheel, and omega R is the angular velocity of the right wheel. Okay. Okay, and then we have a center line here. Okay, And then, so this is our desired input, okay, or reference. So, and then let me call RD, okay, which is the dl plus dr over 2, okay? So this is desired, right? So I want the robot to follow basically this line, okay? So how you calculate this line? So we're gonna measure distance from the left sensor to the wall here, and that's dl, and then dr is the distance between the right sensor and the wall, okay? And the average of these two distances, that is our desired um, distance, okay? So, and then we want our robot to follow this line, okay? Move along the line, right? And then, so this is the desired signal, and then this distance here, this is the current distance, right? And then this is error. Okay, and then our goal is, we want to make the error to be 0, right? So error is E of t, that is r dt. Okay, this is a reference or desired, and then minus drt. Right? So so if the E of t is greater than 0, okay, so E of t is greater than 0, that means the robot is off the right, right? And if E of t is much greater than 0, okay, and the robot is far off to the right, okay? If E of t equals 0 and robot is on the line, okay, on the center line. If E of t is less than 0, the robot is off to the left. If much less than 0, the robot is far off to the left. Okay, so if robot is off to the left, then we need to make a slight left turn, right? That means we need to have omega r, which is the angular velocity of right wheel should be greater than the angular velocity of left wheel, okay? And then we can make a slight left turn. So if it is a far off to the right, then we need to make a sharp left turn, okay? In this case, omega r should be much greater than omega l, right? If it's a center, if it's on the center, then we just need to move straight, okay? In that case, omega r should be the same as omega l, right? And then if it's off to the left, then we need to make a slight right turn, okay? That requires omega r less than omega l. And the last case is the robot's far off to the left, then we need to make a sharp right turn, okay, which is omega r much less than omega l, okay? Well, but but we have 5 different cases, but where is it? Okay, but there are actually, infinitely many different cases, right? Because the E of t is, can be any value, right? Any real number. So we want to have a automatic control algorithm, Okay, so the so then I will propose a controller which is E of t is u of 0, u0 plus kp times E of t. Okay, so in other words, then right motor is going to be the PWM equals PWM 0, right, plus kp times E, and left motor is PWM 0 minus kpe. Okay, so this PWM 0 were u naught here. Okay, that is basically a nominal PWM for average speed. Okay, okay, right. Let's see. If E of t equals 0, okay, then what happens? E of t equals 0, right? And kp, right? So the kp and et becomes 0 because E of t equals 0, right? And then that gives us PWM left equals PWM PWM R equals PWM L, okay? The same as PWM 0, right? That will give us omega R equals omega L, okay? And the robot is going to move straight, okay? If E of t is greater than 0, okay, E of t is greater than 0, then this part becomes positive and this part is still positive, and then we're going to subtract from PWM 0, right? So PWM R is going to be greater than PWM L, right? That gives us omega R greater than omega L, okay? That makes the robot that slide left turn, okay? And now, if E of t is much greater than 0, then PWM R is much greater than PWM L, and omega R is going to be much greater than omega L. That will make the robot sharp left turn. Okay, so you can try the other case is just omega t is less than 0 or much less than 0, right? Okay, so then the next question is then how can we choose kp? Okay, well most time it is trial and error. Okay, there are some systematic method, but still in a lot of different cases they use just trial and error. But the good news is we can easily find a range. Okay, the range of kp, right? Okay, so let's see. Let the error is 10 millimeters or 1 centimeter. Okay, and then let's say PWM 0, PWM naught equals 5,000. Okay, this is again the nominal speed. Okay, nominal PWM. And if KP equals 1, for example, then PWM R equals PWM 0 plus KP times E, which is 5,000 plus kp equals 1 times 10, okay? And then that will give us 5,010 for PWMR. And then PWML is going to be minus kp, okay? That will give us 5,000 minus 1 times 10, which is 400 990. Okay, so so these two differences, it's very small, right? So it will hardly make any changes. Okay, if kp equals 100, then the PWM R is going to be PWM naught plus KPE, which is 100 times E is 10. Okay, so that is going to be 6,000. Okay, and PWM L is going to be the PWM naught minus KPE, is 100 times 10. So that gives us a 4,000. Okay, wow. There's a big difference between the two, right? So it'll make a sharp turn, okay, for a really small error, okay? So the error is only 1 centimeter, okay, very small error, but then we're gonna try to make a very sharp turn, right? So from these two, two calculations, we can easily find that, we need to have, the KP between 1 and 100, okay? But okay, much less than 100 and much greater than 1, right? This is a very simple way to find a range, okay? So you don't have to try something, totally odd, which is like 0.001 or like a KP equals 10,000, right? So from here, you can probably try from KP equals 50, right? And then see, how it works, right? Right, then then let's look at the effect of our KP values, right? So suppose the KP is too small, okay? And then it'll try to, it'll have a hard time making adjustment, okay? So it takes a little bit longer to reach the center line like this, okay? So basically we have a very slow response, okay? And if KP is too large, okay, then we're gonna have fast response, okay? So we're going to try to make a very quick adjustment, right? And then just going, move so fast, right? But the side effect is it moves too fast, and basically we have overshoot, right? So just moving back and forth like this, right? So it has a fast response with oscillation. Okay, but what we want is we want to find, the best KP value. Okay, that gives us a fast response. Okay, and no oscillation. Right. So what we want is something, something fast like this. Okay, faster than this one. You should approach the center line, okay, as quickly as possible, but with no oscillation, something like this, okay? So that's what we want. So okay, so let me show you a movie here, okay? So the first case is very small KP. Right? So you can follow the center line, but it takes a little bit of time, okay, to get to the center line, right? And the next case is I want to increase KP a little bit, okay? Oh, it's much faster response, right? So can you tell the difference? Okay, let's go back to here. So around at this point, the robot is on the center, right? But the second case, as I increase a KP, then around at this point, the robot is already on the center line, okay? So I can just keep increasing KP, right? And then see what happens. So KP is now too large, then what it happens is it is oscillating, right? Okay, so that's what happens. So you're gonna try some different values of KP, and then you can observe how your robot, behaves. right? So if it is oscillating like this, that means, you know, you have to decrease Kp, right? If the response is too slow, like this one, the first case, then you have to increase Kp, okay? And then you want to try and you know, multiple times, and then you want to find the best Kp that gives you the fast response, but no oscillation, okay? Maybe sometimes a very small oscillation is okay, right? But so in our case, in this case, maybe no oscillation would be better, right? Okay. So again, increasing the proportional gain, which is Kp, has the effect of proportionally increasing the input signal U of t for the same level of error. Okay, the fact that the controller will push harder for a given level of error tends to cause the closed-loop system to react more quickly. Okay, but also to overshoot more. Okay. So we have a small Kp, okay, and then here we have a large Kp, okay, and then it reacts more quickly here, okay, but then we have overshoot, right, something like this. Another effect of increasing Kp is that it tends to reduce, okay, but not eliminate the steady state error. Okay, so what is steady state error? Okay, so a steady state error is the difference between the desired value and the actual value of a system when the response has reached the steady state. Reached the steady state, right? So here the system output is moving, right? Here is called transient response, okay? And here, so it's stop moving, or somewhere here, it is a steady state, right? And then steady state error is the difference between the desired value, okay, and then the steady state value here, okay. So this one is a steady state error, okay. And then in this case, the difference between the two, that is also steady state error, okay. So as we increase Kp, okay, then we can reduce the steady state error, right? As you see here, we cannot eliminate, okay, but we can reduce steady state error. But another side effect is if you increase, keep increasing the Kp, then we have large overshoot, or like a more oscillating behavior, okay? So it is limited, right? So the steady state error is mainly came from the non-linearity of the system, such as the Coulomb friction, okay, or the dynamic friction, okay, and then also uh, the the um, the range of sensors, or sometimes non-linearity of the sensors or the actuators. right? Okay, so so this kind of state error is not really good for the system performance. So we want to we really want to reduce, or sometimes we want to eliminate the state error. Okay, so the way you want to do is, so we have proportional control. Okay, and then we want to introduce integral control, right? So integral control, and then now we call it PI control. So the integral control is just basically just we want to integrate the error, okay, from t equals 0 to the current time. Okay, so how does this integral term work? Right? Okay, let's see. So proportional control, then the error is basically at t equals t1. Okay, so the input to the system is a kp times e of t1. Okay, so e of t1, this one is basically just a current error. Okay, the error at the current time, okay, which is t equals t1. And then and then we have a steady state error here. Okay, but proportional integral control is, we have kp times e to t1. Okay, so this is the same as this guy, so this is a current error. And then we also have this integral term, right, to up to t1. Okay, so the error is this one. Okay, and then the previous error will be like this. Okay, all of these are previous errors. So E of t or E of tau. Okay, and then you want to integrate all of these errors. All of these errors. What does that mean? Integrating all the errors is basically the the area of this guy. Okay, so this area here, that is the integral of 0 from 0 to t1 to e tau and d tau. Okay, so by the way, I use tau here. So this is just basically a dummy variable. Okay, so I just don't want to use the same t here. Okay, so e of t is this t should be the same as this t, right? So that's why I cannot use the same variable here. And this tau is just a dummy variable, right? Okay, so the area under here, that is the integral. Okay, so what does that mean? What does this, the area under here, or like a sum of all of these errors? Okay, so that is basically accumulated error. Okay, so or just all the past errors. Okay, or the accumulated past errors. Okay, that's that is this integral term, right? So in this case, so because we don't have that such an integral term, we don't see anything in the past, and we have steady state error. But now we also want to look at all the state the past errors. So if we have, suppose we have these small errors, steady state errors. Okay, so suppose that we have something really small here, steady state errors, right? But the current error is very small. Okay, but accumulated error is going to be huge. Okay, so that's how this integral term works, right? And then because we're going to use all of this past error, then we can eliminate the steady state error, right? Okay. So I show you some plots here. So now I have So next one, let me first discuss different controller here. Okay, so we have integral control, right? And then there should be derivative control, right? So it is Kp times E plus Kd times d of dt E of t. Okay, so just we have a derivative term. Okay, so the way it works is we have Kp equals 250. I just pick some number here. Okay, and then we have really high, really good fast response here, but it is and then but you have a large overshoot or like oscillating behavior here, right? Right. So I just want to just introduce KD, right? So KD equals 0, KD equals 5, and then we can reduce the oscillating behavior here. Okay, and then if I just increase KD a little bit more, okay, then basically you can just push this thing down. Okay, so push down here to get less overshoot. Okay, less oscillating. Okay, and then if I have a little bit more KD term, then whoa, we just have a really small oscillation. Okay, or like no oscillation and then very small overshoot. Okay, so as KD goes up, the overshoot goes down. Okay, so the derivative term is basically we are adding more damping. Okay, or in mechanical systems we are adding more friction. Okay, in electrical systems we are adding more resistance. Okay, so we are adding damping. Okay, so then it's really hard to oscillate. Okay, so that's how the derivative term works. But now the problem here is we have steady state error. Okay, so let me call it ESS. Okay, looks good, but there is a steady state error. Okay, so but we know how to fix this, right? So we're gonna use integral term, then we can fix this steady state error. Okay, now let's look at PID or proportional integral derivative control. Okay, so it is just simply it is just a proportional term. Okay, and then the integral term. Okay, and 0 to t, and then kd over d over dt e of t. So derivative term. Okay. Okay, so if you have open loop system, no feedback. Okay, so we may have the desired the value, but with any disturbance, the performance is going to be really poor, and then also the response is very slow. Okay, with Kp, okay, so Kd, Ki is still 0, so the proportional control, okay, we can make a system fast. Okay, so and then but the problem is it is going to oscillating a lot. Okay, so the main goal of Kp, the proportional control, is to make the system fast, right? And then now let's introduce Kd. Okay, and then the system is still fast response. Okay, and then no oscillation. Okay, or no overshoot, but we have steady state error. Okay, so now we have a PID control. Okay, so all three terms. Then we have very fast response. Okay, and then we have no oscillation. Okay, and then we have no steady state error. Okay, no steady state error. Okay, so that's why we use PID control, right? So the PID control is used a lot of different places, like automotive, the aircraft, and some robotics, and many different places, right? Okay, I'll show you this movie. Where is it? This is a pretty nice video, but somehow, there's no sound, right? I mean, the guy is not talking. Okay, so this is basically a motor control, right? Or maybe if you're familiar with, this is a servo control. Okay, so we have he has the proportional control with Kp equals 200. Okay, so it has a steady state error. Okay, so now I change it to from 220 proportional control. That is 200. Okay, so there is a steady state error, and also a little bit of oscillation. Okay, so now the proportional gain is 500. It was 200 before, now it's at 500. It's much faster, but it has a much more oscillation, or like overshoot. Still has a little bit of the steady state error. It's very small, but still there's a little bit of steady state error. Okay, and then now with the derivative control, then there is no overshoot, right? There is no oscillatory behavior, and they're very fast, but still some steady state error. Okay, now that integral term, which is 400. Okay, so now it's Kp and Ki, so Pi control, right? So it always goes to 0, right? So which means that there is no steady state error because of a Ki. So now, now we have a PID. Okay, so Kp, Ki, and Kd. So this is a little bit more like an advanced one. Okay, there is something called anti-wind up that I have not discussed it, here, but we don't have to worry about that. Okay. All right. So Kp is too large. Okay. 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 So the controller is now running at 200 hertz. Okay. So that means I'm going to discuss a little bit later. So you need to have a timer. Okay. And to run a controller, and then the timer frequency in his case is it was a 500, it was a 100. Now it is 200 hertz. Okay, so basically it updates the control input more often than before. Okay, now it is 800 hertz. Okay, it's really good, right? So that's really nice and good performance. Okay. Okay. So derivative control. So we are not going to use the derivative control in module 17, and you probably do not want to use any derivative terms in this class. Okay. The reason behind that is the noise. Okay. So let's look at these 4 different plots. Okay. So the first one is the sine wave without noise. And the second one is a noise, but a standard deviation is 0.001. It's very small. And also, this is a noisy sine wave with a standard deviation of 0.005. And then the next one is a 0.010, right? So you can see some noise here, right? So it's a very noisy measurement, okay? But still, you can think this is very small noise, okay? And then if you take the derivative of this signal, what will happen? So this is a sine wave, okay? The derivative of that is going to be cosine, and something like this, right? So how about this? So this is going to be something like this, right? But because there's a noise, so let's just zoom in this area, okay? So this is a pure sine wave, okay? And then the noise signal is going to be something like this, okay? And then if you take the derivative of a noisy signal, and I guess what happens? The derivative of this, okay? Or that, or this, okay? So the derivative is basically the change in time, right? So change from here to here is something like this. And then here is like this, all right? So if you take derivatives of these four signals, this is what you're gonna get, okay? The first one, yes, no noise. Yeah, you have a cosine signal here, okay? A little bit of noise, it's really, really small noise. And then you have, this kind of signal, okay? And then now with a 0.010, the standard deviation of that small, then you have pretty much, nothing, okay? So basically, derivative terms, they amplify noise, okay? So, well, so, a lot of time that, in physics, that you learn that A, the acceleration is dv over dt, right? You just, derivative of velocity is your acceleration, and v is ds over dt, okay? So, well, this is true, but if they are measured signals with the noise, then if you take derivatives, then it becomes useless, okay? So this is what happens then if you have a GPS signal with a noise, and then if you take derivatives, then it doesn't really give you good velocity information, right? So the rule of thumb is if the information is measured, the signal is measured, using sensors, and then it has a noise, okay, and then you cannot derivative, okay. So that just gives you a lot of noise, okay. So then our sensors, okay, are very noisy, especially the tachometer and the distance sensors. They are very noisy, so you don't want to take derivatives, okay. So please do not use derivative control. Okay, so now, okay, we're almost there. Okay, so everything we discussed are all in the continuous domain, okay? But we're gonna use a MSP 432, which is a small computer, and then in a computer, everything is everything is a discrete time, right? So we really cannot use this continuous model, okay, or continuous time control method. So we need to, to implement that in a computer, then we need to discretize. Okay. So control law is now, should be in discrete time. So instead of a t, okay, instead of a real number, we need to have k. Okay. So this is an integer or like an index, right? So kp times e of k, okay, times ki And so this integral in the continuous time domain, okay, becomes a summation in the discrete time domain. Okay, so what it means, we have a summation of n equals 0, okay, of k up to k, and then e of k plus e of k minus 1 over 2, which is basically the average of these two, okay, and then delta t, okay. So I hope you remember from your calculus, I don't know, maybe calculus 1 or calculus 2, okay, if this delta t goes to 0, approaches to 0, okay, then the summation becomes the integral, right? So with a small sampling period of delta t, okay, sigma is a good approximation of integral, right? So and then again that as delta t approaches 0, okay, then sigma becomes integral, right? So now we're going to use sigma instead of integral, right? Okay, but sometimes I don't like sigma because I have to just accumulate all the past, measurements. Okay, so this is a quick trick that that we want to use. So we know that u of k is given by this first equation, right? Then u of k minus 1, okay, should be given by e of, kp times e of k minus 1, same as that, right? And then the summation, so the k should be this. Oh, sorry, this one is n, right? Because n goes from 0 to k, right? They all should be n, okay? Right? So this one is now, it should be, u of k minus 1, okay, is given by kp times e of k minus 1 plus ki. This is the integral gain, and n equals 0 to k minus 1 instead of k. Make sense? Okay. Then now, let me subtract this guy from the first equation. Okay. Then what we have is a u of k equals, or u of k minus u of k minus 1. Then we can move u of k minus 1 to the right side. Okay, so u of k equals u of k minus 1 plus kp. Okay, these two terms, kp of ek minus e of k minus 1, right? And then plus these two. Okay, so I want to subtract this guy, this one, from this one. Okay, but if you look at this one carefully, so ki times the sigma n equals 0 to k is basically the same as n equals 0 to k minus 1 plus, and plus the k terms, right? So that gives us that e of k plus e of k minus 1 over 2. Okay, so then we can get rid of the summation. Okay, or okay, we can rewrite this equation to e of k equals u k minus 1. Okay, plus, let me just introduce a new variable, which is ka of ek plus kb of e of k minus 1. So this is the current error. This is the previous error. Okay. Then where ka is, look at the e of k terms. Okay. So ka is kp from here. Okay. And then e of k term is, I have a ki, okay, times delta t over 2, right? So Ki delta T over 2. And Kb, this one, it is E of K minus 1 term. Okay, so this term is a minus Kp plus Ki delta T over 2. Okay, so basically if you look at Ka and Kb, so Ka is a sum of the Kp and Ki, right? So sum of the proportional gain and the integral gain. And then Kb is the difference between the integral gain and the proportional gain. Okay, so in general, Ki is greater than Kb. Okay, or in many cases, Ka is much greater than Kb, right? So now, then with this equation here, then I don't have to keep track of the order like a past errors. We can just look at the current error and the previous error. Okay, with these two errors, okay, the current error and then the previous error, then we can implement proportional and integral controller. Okay, so in your code, something like your controller. Okay, so UR is the PWM to the right motor. Okay, should be given by UR equals UR. Okay, so this is basically like past the PWM signal, which is a U of K minus 1. Okay, and then Ka times error R, okay, plus Kb times previous error R, okay, and then the PWM to the left motor should be UL plus Ka times error L times Kb times previous error L, okay, and then you need to save the previous error to the next iteration. Okay, and then this controller here, this guy, this function must be called every delta t second. Okay, so this is a period by who? So the timer, or by timer interrupt. Okay, so basically you need to put this thing in the timer handler. Okay, right. Okay, the last slide. So, okay, module 17, okay, is basically we're gonna find Kp and Ki, right? Or Ka and Kb for the best performance. And remember that this is the crucial part of your final project. Okay, and the speed control 7.1, program 7.1 is a speed control. Okay, so basically it is a cruise control system. You want to maintain a constant speed of your wheels. Okay, so you're going to use a PI control, okay, proportional integral control, right? Then as I discussed before, then you're going to use U of K equals U K minus 1 plus Ka times E of T and Kb of E of K minus 1. Okay, so you have two gains, two variables to tune at the same time. Okay, but just start with Kb equals 0. Okay, and then change Ka until you have a good performance. Okay, so and remember that Ka is much greater than Kb. Kb is a very, very small. Okay, so with maybe like with Kb equals 0, so you probably get what you want to get, right? So spend more time on Ka, right? Okay, program 17.2 is wall following. Okay, this is the one that I showed you in the video. Okay, so that is world following, so that you need just proportional control. But in this case, you need to have a u naught, okay, for this nominal speed, okay, plus kp. And then the third one is a line following. Okay, so you need proportional control, and you still need u naught, and then different gain, but still a proportional control, but not the same value here. Okay, so it should be a different value. And this u naught again, this is just a nominal PWM. Okay, and then this nominal PWM will provide the average speed of the wheels, right? Okay, so this is module 17, and I'm sorry that this video is very long, but I try to make it short, but this is basically the best performance I could, right? Okay, so have fun with the lab.